All right. So in class, we talked about how common the sine function is in ECE. And we gave a couple of examples. Radio waves are one common one that you'll learn a lot about in your junior year when you take fields and waves. And we can think of things like AM radio signals, FM radio signals, satellite radio signals, your cell phones, communication signals. All of those have a sinusoidal nature, right? So those are common signals that come into circuits. Sound waves come into circuits, and those are also sine waves, as we saw. Magnetic fields and rotating machines, which really drive electrons through our power systems, those also take the shapes of sinusoidal functions. And all of these are sinusoidal functions of time. Okay? So we'll look at that a little bit more carefully here with a specific example of magnetic fields. Now, those three examples, radio, sound, magnetic fields, and rotating machines, those are all basically examples of analog things that electrical engineers think about. But I could take those sound waves, for instance, and I could sample them. So I could convert them to digital waveforms that would exist in some sort of digital media, be it a hard drive or a RAM or a flash, and they'd still be sinusoidal. Okay, so we'll think about that kind of thing later too as well. So it's important to know that this is important for both electricals and computers. Now, let's look at the example of a generator. So what I have here is a picture of a basic three-phase generator. All right, so the generator is shown on the left, sort of a cross-section of it, and then the voltages that are produced are shown here on the right. So let's focus for now just on the generator itself. So what I have in the middle of the generator is a rotating magnet. Okay, so the magnet rotates around, and it's being rotated by some kind of a turbine that we don't see. Remember, this is a cross section. So somewhere behind the screen, there would be a turbine driving this thing. And that turbine would either be driven by steam, or somehow there would be an engine that would be combusting natural gas that would be making that guy spin around. Okay, so that's where the energy's coming from to make that guy move. Now, what I have on this machine is basically that rotor there with that rotating magnet is moving around inside of this stationary piece of iron. So this sort of grayish thing here is something we call a stator, but it's a stationary piece of iron. And what I see is that there are three sets of coils that are completely independent from each other. The red one here is the A-phase coil, the green we call the B-phase coil, and the blue is the C-phase coil. So remember, we're looking at a cross section. So basically, I have a coil coming out here, and that same coil is coming back down the side of the machine here. And I basically have three sets of coils like that. So let's just look at the red. Let's just look at the phase A for now. And let's draw this out slowly. So let's say I stopped everything where the machine looks like it is right now. So I've left only the phase A coil. And note the way I've drawn this, right? I've said I've got coil coming out here at the bottom. That's what the circle coming out of the screen means, that that coil's coming out. And that X up here means that the coil's going back in. And again, we're looking at a cross section. But given the way this guy is set up right now, I would say that that magnet, whenever I have the north pole pointed like this and the south pole down here, I'm going to say that that rotor is sitting at theta equal to 0 degrees. So the angle of that rotor, I'll say, is 0 degrees. Now, if he turns himself like this, then I'll say the angle is 90 degrees. Okay? So notice that he's turned himself. The north pole has rotated 90 degrees. So here he rotates another 90 degrees. So I'll call that, say the rotor is at 180. Here I'll say the rotor is at 270 degrees. So that rotor keeps moving around. And if I waited a little longer, it would come back to this position, which is also, I could say, 360 degrees. Okay? So let's look at this condition for now. Now, if you know anything about magnets, and you should from your days in physics, if I look at a magnet and I have a north pole here and a south pole here, you should know that magnetic field lines leave at the north pole and return at the south pole. Okay? they leave at the North Pole and return at the South Pole, they're always closed on each other. In other words, magnetic field lines don't just go off towards infinity. They're always closed loops. And they would just sort of wander out and get a little bit weaker as they went further out. And this guy will end up being kind of symmetric, more symmetric than my bad drawing can make it look, at least, right? But they're always leaving at the North Pole and exiting at the South Pole. Well, the big reason for putting this big stationary piece of iron on the outside is that big stationary piece of iron guides the field. So I got a field line that leaves at the North Pole and is guided through this stationary iron like that. So the whole role of that iron is to basically guide that field through the machine. All right, and you can learn a lot more about machines in later classes, right? If I look at this scenario right here, with the way that magnet is sitting at theta equal to 0, if I look at the coil here, and I drew the plane of the coil. So the plane of the coil would basically be a line that kind of cuts from the top of the coil to here. What I see is that no field is passing through that coil, okay? So in this particular case, there's actually no B field, no magnetic field that cuts through the plane of that coil. So if I call the B field passing through that A phase, if I call that BA of T, at this condition I see that there's none. Now if I rotated that coil to 90 degrees and I redrew my field like this, as it would be in that scenario, all right. Now if I look at that, I have a whole bunch of field cutting up through the plane of the coil. So the plane of the coil runs straight from the top to the bottom of the machine. I have a whole bunch of field passing through here and then coming back up again. In fact, I would say that that's the maximum amount I could have, and I'll call it B max, okay? Now, if I look again at 180 degrees and I draw my field lines again, it's a bad field line, but it's a field line. That one's a little bit better. All right. Again, if I were to draw that plane of the coil from the top to the bottom, I would see that in this case, I also have, in this position, basically zero field passing through the plane of that coil. If I go to 270 degrees, I've got a pretty similar situation to what I had at 90 degrees, right? I have a lot of field passing through that iron, right? I have a lot of field passing through the plane of this coil, but it's going in the opposite direction as what it was doing at 90 degrees. So in this case, it's the maximum amount that can pass through, but it's doing so in the opposite direction. So I'll say the field strength is negative. It's pushing the other way. So what I can see here is that if I look at my theta and I look at my B of T, and I do it for 0 degrees, 90 degrees, 180 degrees, 270 degrees, and also 360 degrees, I saw that at 0 degrees I had no field, at 90 degrees I had the max, at 180 I had 0, 270 I had the max but go in the opposite direction than I had at 90, and at 360 I should be back to where I was at 0 degrees. So what I see is that it looks like that B field in that A phase coil basically follows something like this, right? It looks like the B field follows the sine of the angle, okay? So in other words, at 90 degrees, it reaches its maximum. At 270 degrees, it matches its negative maximum. And then at 0, 180, and 360, it's 0, okay? So it sort of follows a sinusoidal shape as a function of that angle. And in this case, because of the action of that turbine, If I rotate the turbine at an angular frequency omega, then theta equals omega t. In other words, the angle of the rotor advances at a rate of omega. Okay? And in the North American power system, omega would be 2 pi times 60, right? 2 pi times 60 hertz. Okay. Now that I know that, if you go back to your physics, basically what you find from what we call Faraday's law. Faraday's law basically tells us that there will be a voltage induced in that coil on the stator, and that voltage is proportional to the rate of change of the flux passing through that guy. So basically the rate of change of the magnetic field times the area. Now the area doesn't change, so I write this as area times dB by dt. And I say dBA because I'm talking about the A phase, right? So if I were to look carefully at this guy, this becomes A times d by dt of what I had before, B max sine omega t. What I end up with is A B max over omega cosine omega t. So it follows a cosine function. So that means the voltage that's induced should be a cosine, and a cosine as a function of time would look like that. Okay? So if I go over to this picture now, let's see what's happening. So I can see from here the red line tells me the voltage at any given time. Okay? So as I follow that red dot there, as that red dot goes up and then back, it's telling me at any given point, so we're based on wherever the rotor is pointing at a given function of time, or at a given point in time, that red dot tells me what the voltage would be at the terminals of that coil. Okay? So the interesting thing is we see that the voltage follows a cosine shape, just like we said it would. Okay? So the voltage follows that cosine shape. And we see that as the rotor advances along, right? As the rotor advances along, I can see that the voltage out of that machine would change. Now, I noticed that this is a three-phase machine. Okay, so I explained one of the voltages. If you look, it would appear that this, say, phase B coil looks like he's been turned 120 degrees. If you look at this carefully, and you'll learn this later, looks like he's been turned 120 degrees forward, and that the C phase coil has been turned basically 240 degrees forward of the A phase coil. As a result, it takes the voltages and shifts them from A to B 120 and from A to C 240. Okay? So you'll learn more about that in other places, right? I just wanted to mention it. Important thing to kind of take away from this is, again, this is kind of a little bit of a hand-wavy argument. You can get into a lot more detail about all of this stuff. But the important thing is this should kind of explain a little bit as to how we end up getting sinusoidal voltages in our systems. We could have this machine produce maybe a different type of waveform, but as you'll find out in your other courses, if I did that, this machine would actually be somewhat inefficient. Sine wave output voltages make the machine very efficient, and so it's pretty common for us to do it. So you'll learn a lot about sine waves in physics, sine waves in circuits 2. And even if I do have more complicated waveforms, what I find out is I can view those complicated waveforms as having sine waves inside of them. So we'll talk a lot more about that later. But I wanted to give a little bit more context.